Hey, welcome to Rational Functions. I know you're all excited about it, so am I. We've talked about rationals in the past. We've added them, we've solved them, we've simplified them, multiplied, divided, etc. So now we're going to get into graphing of them. Um, so the objective for today is that if you have any rational algebraic function, you're going to simplify it, and then from there, you're going to find something called discontinuities, and then you're going to draw the graph. And just so you know, as a heads up, there are two different types of continuities, and we'll talk about both of those. And the first ones that we're going to do here on the first day are going to just have, are going to be somewhat on the simpler side. The second podcast goes back into what happens if you have multiple asymptotes, as they're called. And then we've got some other fun for you after that. So I know this is going to be a little different than how I normally do it. I'm going to go ahead and show you the 4 steps first, and then after that, then we'll go ahead and show you an example. So the first step in graphing rationals is going to be you need to find the vertical asymptotes and the removable discontinuities. Now, the removable, these are, we've already seen these. These stem from the places where you have domain issues. Okay, so as an example, you're going to see stuff if I had, let's say, 3 over x minus 4. You know, x cannot equal 4. That is going to lead to asymptotes or the discontinuities. Removable discontinuities, like we talked about before, are going to be the ones that you can actually divide out. Those are like those pesky ones. The vertical asymptotes are the ones that, you know, stay around the whole time. We're going to plot the vertical asymptotes. After we're done with that, and obviously if you need to pause as we go through this, please do so. Whoa, wrong button. I deleted the whole page. That was fun. All right, anyway. Come on, where are you? Undo, delete page. There we go. Sorry. You know, if a teacher who, you know, really cared about what things look like would go back and just hit stop and keep going, but no, I'm not perfect. All right, anyway, so now the next thing you're going to do is you're going to find the horizontal asymptotes, okay? The asymptotes, again, are lines that you get infinitely close to, but you don't actually ever touch. And we've talked about those kind of in the past. So we're going to find the horizontal ones, and as soon as you see them, you'll be like, oh, yeah, I remember those. So step 1, find all the vertical issues. Step 2, find the horizontal ones. For step 3, we're going to find function values of the x values centered around the vertical asymptotes, and we're going to plot your points. This is the long way of saying, hey, we're going to plug in points and make it look pretty. The important part here, though, is that you're going to center them around your vertical asymptotes, much like the points that we picked to plot parabolas centered around the points of the x values of the vertex of the axis of symmetry, and also much like you would do when we were plotting polynomials and we were finding, you know, good points that were falling between the zeros. And then lastly, you're going to sketch the polynomial. Actually, sketch the rational. What was I thinking? Bad, Mr. Hayes. And you're going to finish by including the removable discontinuities. Remember, the removable discontinuities are those places in the domain that don't look like they actually are in the function, but actually are. All right. So wow, this has been stellar. I delete a page. I miswrite something. Teacher of the year. All right. So if you're not ready, you're still copying this down, hit pause. I'm moving on. I'll see you on the next page. All right. So remember, step 1, you're going to simplify this. So what we're going to do first is that we're going to go through and we're going to factor out the bottom. The bottom is going to factor out to be x minus 5 and x plus 8. Now, here's the place where you start determining what's going to be a vertical asymptote and what's going to be removable. Now, if you remember before, what will end up happening is that the x minus 5 is going to divide out, because this is a whole entire expression. That's going to go away, and that's going to go away. So this expression is going to normally be, it's going to act just like 1 over x plus 8. However, remember with the domain issue, we would say, okay, x cannot equal 5 and x cannot equal negative 8. The difference here, however, this one is the removable one. Why? Because guess what? We removed it. So that's our removable discontinuity. So we're going to come back to that at the very end. The other one is something called a vertical asymptote. We will normally abbreviate this VA, but a vertical asymptote, remember, asymptotes are things that graphs will approach but never actually touch. Okay, so now that we have that x minus 8 is my vertical asymptote, if we go back, remember, it says we're going to plot the VA here. Okay, so we did this, check, plot the vertical asymptote. So now we're going to go through, and at x equals negative 8, now first of all, remember, label your axes. You don't want to be one of those people who don't do that, because that's just rude to your reader. And again, you know, you potentially could adjust this as you go, but at least, you know, we know left to right we're going to be counting by ones. We're going to draw in a nice dotted line at x equals negative 8. This is kind of like that little brother theorem we talked about, how you can get infinitely close to it but not actually touch it. Kind of like, you know, the I'm not touching you, I'm not touching you, I'm not touching you thing. Right. All right, so we did that. Removable discontinuity, we got rid of it, sent it down to the dean's office, however you want to think about it. We're still making a note. It was here at one point. Vertical asymptote is also here. Now if we go back to step 2, find the horizontal asymptotes. Now the horizontal asymptotes is where these things are going to go, because just so you know, over here on the side, okay, normally what ends up happening, actually I'll make a new slide quick, on purpose this time. What will end up happening is that you get things like this. Rational expressions look a lot like, well, actually they are hyperbolas. They're specific types of, not hyperbolas. So what ends up happening is that whereas you do get removal or asymptote that looks like that, so this, you know, gets infinitely close to that, you're also going to get one that's horizontal, okay? And so like in this case, you know, it's basically where the thing plateaus out. And we've talked about that too. It's kind of like in the long run, what's going on with this expression, okay? So, see, this is why you don't freehand things, boys and girls. So, you know, as x gets infinitely large or as it gets infinitely small, what is this graph doing? The most interesting stuff always happens around the vertical asymptotes. The most boring stuff happens out like at 1 billion or something like that. But you can do this a couple of different ways. To find a horizontal asymptote, what you can do is this, okay? Horizontal asymptote, horizontal asymptote. Okay, part A, this is one way to do it. So as x goes to infinity, my function goes to what? So in this case, as 1 goes over x plus 8, as x gets larger and larger and larger and larger, it's going to have more and more important role. So the first way to talk about it is to say, okay, if I plugged in, let's say, like 1 billion in for x, okay, that's going to go to 0, because you're going to get, like, you know, 1 over, you know, pick your favorite large number, and that's going to be basically 0. So in this case here, this is your horizontal asymptote. Okay, that's my HA. And that's what we're going to draw in. So as x gets bigger and bigger and bigger and bigger, it's going to flatline and it's going to get infinitely close to, but not touch the x-axis, because you're always going to have that 1 up in the top. But for all intents and purposes, it's going to touch the x-axis. So we'll draw one in, adjust it as necessary. Ta-da! And we're done with step 2. Yay! So if you're playing along at home, which of course you are because you're doing this as a podcast, Step 1, done. We found the vertical asymptotes and removables. Plotted the vertical asymptotes. We found the horizontal asymptotes. And now we're going to do step 3, find function values centered on that. So all you're going to do, you know, I'm going to make this full. Let's see. Zoom entire page. Hopefully you have a big screen computer and you're not doing this on your phone. If not, zoom in as needed. But this is basically the last thing. So for step 3, what you're going to do is you're going to make a little t-chart. You can do it on the calculator table as long as you type it in correctly. Biggest mistake that people make on this is they type it into your calculator incorrectly, and then you get things wrong, and then you cry, and you think the class is awful, and it's really you're the person who made the mistake. All right, -8 can't go anywhere because you're going to get 1 over 0. So I would plug in -9, -10, so those are 2 points around it. I would also plug in -7, -6. So when you do this, the -1, you're going to get a -1/2. Plug in -9, I get -1. I plug in 7, and I'm going to get 1, and I'm going to get 1/2. Now, the symmetry that you're seeing here is always going to happen with the following respect. The numbers are opposites because we're centering our horizontal asymptote on the x-axis. If it was off the x-axis, like an example that we'll be doing in a little bit, you'll be the same distance away from the horizontal asymptote. So you will still see, when you look at it, this sort of strange symmetry. So anyway, here at -10, you're going to have like -1/2. Here you've got -1. Up here, we've got 1, and we've got -1/2 here. And you'll actually end up, if you were to go through and find half points here, the half point would be like up here at 2, you'd have 1 over here, and so you're going to get this nice graph going like this, and you have a nice 90-degree sort of hyperbola thing going on. Like that. Now, so that's step 3. Now, step 4, remember, is your removables, right? Now, remember, according to our domain, discontinuity. According to our domain, what ends up happening is x can still not equal 5. Okay? Come back here, highlighter, so don't forget that. So when we draw this out, okay, even though we're effectively equal to 5, you're going to have to put an open circle there because it can't actually equal 5. And if you were to plug that in, so actually, you know, if x equals 5, y is going to equal 1 over 5 plus 8. And get 1 over 13. So, I mean, for all practical purposes, when we draw this, it's basically on the x-axis. But, you know, you still need to include it because it's an important thing. You don't want to shortchange anybody or anything. But anyway, so that's it. 4 easy steps of graphing rationals. Find your asymptotes. Find your horizontal, both vertical and horizontal. Find your removable discontinuities. Plot some points, and then make sure you put the discontinuities in. So let's try another one. Ooh. Now this one. Hi, I'm back. Decided to call an audible. Changing this up a little bit to make sure we are where we want to go. I put it in factored form, assuming you guys already know how to factor it. So for step 1 here on this one, so again, we're going to label all the discontinuities, give the domain a range, all that other good stuff. So what ends up happening here is that I've got, okay, f of x is equal to x plus 3 times x plus 4, x minus 2, x plus 4. So which one is the removable discontinuity, and which one is your vertical asymptote? Those go away. So you've got a removable discontinuity at x equals -4. So somewhere where we have x equals -4, we're going to have an open circle. We have a vertical asymptote at x equals 2. So I'm going to draw in my nice dotted line at 2. Oh, I forgot. I know you're screaming at me right now. Label your axes, Mr. Hayes. Good point. X, f of x. I know some of you are screaming too because this podcast is longer than normal. You guys are worth it. Don't worry. So now at this point we need to worry about, so this is going to act like x plus 3 over x minus 2. Okay, the graphs are going to be identical with the exception of the removable discontinuity, which we'll get to at the very end. Now for your horizontal asymptote, by the way, the secret word today is Amsterdam. So the horizontal asymptote, what we're going to do is this. Now again, you've got two options. So again, what is x plus 3? So as x goes to infinity, x gets, and this, by the way, is kind of really the start of some of the stuff you guys are going to do in terms of limits and pre-calculus and calculus. And it's one of those things that's not a hard concept to get. It's just a matter of getting used to it. So as x goes to infinity, what is the function doing? Well, as x plus 3 is here over x minus 2, as x gets larger and larger and larger, what two parts are going to have the most influence on what's going on? The x values are going to have the most influence of what's going on. Because think about it. If x is equal to 10 billion, let's play federal government. Okay, so if x is equal to a trillion, do you think $3 and $2 is going to really make a difference? No. Okay, which is why you get, things like the president saying, well, a few $1 million saved here and there, it doesn't really make a hill of beans worth of difference in the budget. Why? Well, because when you're talking about trillions of dollars, millions are still like less than 1/10 of a percent. So remember, a trillion is a million. But anyway, so one way you could do is you could plug in like, a billion or something. So you're going to get, oops, sorry, forgot to change that out. Anyway, so if you plugged in a very, very large number, so let's say I plug in, let's say 100,000. So that becomes 100,003 over 997,998. You're going to get a number that's effectively 1. Okay? The other way that you can do it is if you look at just the important part, what does x over x reduce to? 1. So either way works. So if you can just take the highest degree in the numerator and the denominator and then reduce it, that will tell you where you're going. Or if you just want to plug in a really, really large number for now, that also works. But regardless, you have a horizontal asymptote here at 1. So we have to plug in a horizontal line at 1. So again, we will make our pretty line here, come through here, and that's going to be where our horizontal asymptote is. So now all of the information that we're going to go is going to be centered around, when we make this table of values, around x equals 2. So for step 3, okay, I'm going to do a horizontal chart here for sake of room so I don't make this much smaller. Okay, at 2, I don't have anything because that's my vertical asymptote. I'm going to go a little bit to the left, so 1, 0, and let's even go negative 1. And then I'm going to go 3 points to the right, 3, 4, and 5. And then I'm just going to plug values into the equation. So for 1, I'm going to get 4, because I'm going to get 1 plus 3 over, or actually negative 4, sorry. If I plug in a 0, I get negative 3 halves. If I plug in a negative 1, I end up with a negative 2/3. If I could write it down correctly. There we go. And if I plug in a 3, I get 6 over 1. If I plug in a 4, I get 7 over 2, so 7 halves. And if I plug in a 5, I get 8/3. Now again, you might be saying, hey, wait, I thought it was supposed to be all symmetric. Well, it is. Just watch. As I plot out these points, negative 1, negative 2/3, so right about there. 0 goes down to 3.5. And then this is at negative 4. So notice here, oops, not far enough. So notice this point here, if I'm looking at, let me get out my magic pen. This distance here is 5. This distance here is 2.5. This distance here is about 1 2/3. Okay, that's going to be the same distance as over here when I plot out the point 3, 6. 3, 6 is 5 points higher than my asymptote. The point 4 and 3.5 is going to be right here, which is 2.5 higher than my asymptote, just like the other one was 2.5 below my asymptote. and the other one is going to be 1 2/3 higher than that. And then we've got our beautiful asymptotes that we can draw in. Now, the other thing that you have to remember is that we have it to remember, nice, redundant, is that you've got this removable discontinuity here. And so when I plug in a -4, so at -4, I'm going to have a -4 plus 3 over a -4 minus 2. So that's going to give me an answer of actually -1 over -6. So I'm going to get an answer of 1/6. So at -4 and 1/6, so right about here, I'm going to have an open circle for my removable discontinuity. And if you want to mirror that on the other side, that's fine. You just wouldn't be removable. But in terms of drawing it in, it'll be nice. And then you've got a very, very lovely graph that's going to look like this. And again, it's one of those things where, is it a little bit of work? Yeah. But the things that, are worth it in life take a little bit of work. I'm over my 20-minute time limit, so I'm going to leave it here. That should be enough to get you things started. If you want to take a look at the problems off the website, that's fine. Otherwise, we'll start working on those in class tomorrow. And I'll see you then. Thanks.